award for having the most students attending a presentation so far this semester. So congratulations. I want to welcome you all to UW Clare's Faculty Academic Staff Forum. My name is Erica Benson. I'm the Executive Director of the Office of Research and Sponsor Programs, and I am delighted to introduce today's speaker. Dr. Robert Lodge has 17 years professional experience in mining and mineral exploration in academic, government, and private industries. Since arriving at UW Clare in 2014, he has established himself as an expert in sulfide mineral resources in northern Wisconsin. And he's going to tell us about his work with old rocks today, finding the haystack when you need the needle. Before I turn things over to Dr. Lodge, I will note that we'll have some time for questions and comments after the presentation. So this is your assignment to begin thinking about what you might want to ask. And to our online viewers, we invite you to submit your questions using the Q&A function. And our wonderful graduate assistant, Matt, will read those questions aloud to us. When we do have questions from the audience here, Dr. Lodge, I want to ask you to please just give a brief summary repeat of the question for the benefit of our online viewers, because the microphone doesn't pick up everybody's voices. So
got it.
On that note, I want you all to give a warm welcome to Dr. Robert Lodge.
Thanks, everybody, and thanks for having me. This is actually the second time I've given an ORSP faculty forum, so things have progressed since last time I gave this. So I try to keep a lot of this presentation is actually going to be set around the narrative of how hard it is for us to find our metal resources. And then at the end, I'll highlight a little bit of what we're doing to get better at finding our resources. It's going to be impossible to highlight all that research. And so if I don't highlight your specific research in this process or even ongoing research, I apologize for that. But the story is developing and ongoing, and it's actually hitting a really good stride here at the moment. Anytime you give a research talk, this is not going to work. Okay, fine, I'll stay here. You have to acknowledge the people that help fund that. I haven't had the greatest success in getting extramural funding. So my early days here, ORSP grants have funded a lot of student projects. I've done some collaborative work with the Wisconsin Geological Survey and the United States Geological Survey. And then other collaborative work between my Canadian university friends at Lakehead and Laurentian University, which I didn't put up here. The Ontario Geological Survey has given me a lot of lab resources to get these research done. And most recently, Wisconsin System, or WISIS, has given me an IGNITE grant because my research has implications for generating wealth or economic benefit to the state of Wisconsin. I also am taking credit now for a lot of student work. And again, if you didn't make the list, my sincere apologies. I tried to keep the list of people that were actively working in Wisconsin. But we've done a lot of field work, a lot of lab work, a lot of core. And if I had to mental math it right now, about 20,000 linear feet of core have been analyzed by my students since I've been here. So they've been working hard, and the benefits from my research program, I couldn't have done it without them, and I will always do it with them. So now, the narrative of the talk, it's in the title, Finding the Needle in the Haystack. You've all heard it, you've probably used it, right? The idea that a needle in all that hay is going to be really hard to find. And I bet many of you right now are scanning this image to find the needle. And I'd spent probably more time than I should have trying to find the needle in it as well. And there's you guys can imagine just digging through the haystack trying to find the needle, or you'll burn it down and find the needle that way. Right? That's one way of getting it done. But imagine trying to find the needle using a needle, stabbing into that haystack with something tiny, trying to intersect that needle, all right? That's the challenge that we're up against when we're looking for our metal deposits. It's not just finding the needle, it's with the tools that we have to find the needle with. And so in this image of northern Wisconsin is the largest sulfide ore body that we know of in the state. That if we were to start mining it today, it would supply us with copper, zinc, lead, silver, and gold for 40 years. And this is the size of that ore body on this map. So imagine now trying to find that with the tools that we have available. And I'll have other analogies, but this is our needle in the haystack. It's vegetation, lakes, and we can't even see the bedrock. So it's an extremely hard thing to even begin to find our mineral resources to get our metals. And if you don't think we need metals, you can use this image to gauge how much we actually consume. This is Shanghai, China, 1987 to now, all right? Those buildings were not grown in farms, right? They were built with minerals and metals that we mined out of the earth. And there's a science building going up next door, right? All the metals and materials in that building are mined out of the earth. And so we are, as we develop not only as locally, but internationally, as there's new buildings, new factories, new anything, metals are needed to make that infrastructure. We also need energy. I'm presenting right now, and there's lights on, and it's warm, okay? Wisconsin, although it's getting nice out, is not known for its warm weather necessarily, although it is the hottest place I've ever lived. Where do we get our energy from? As much as I would like to say renewables is where we're getting it, all right, fossil fuels are still the place and the most reliable place we get our energy. If we cannot stop consuming today our fossil fuels because there's nothing in the chute yet to replace that energy. And so the breakout of renewables shows, we're increasing our ability with solar and wind, and that's a great thing for obvious reasons. Because, well, we're definitely not doing great things to climate. Our consumption of fossil fuels is putting CO2 concentrations in the atmosphere beyond anything that we can see in the past 1 million years. And it's very rapid. There's not a linear scale on the bottom here. What we see is that it's a logarithmic scale, in fact, and that when we get to the Industrial Revolution, that's when things really take off, all right? We are consuming, anybody drive from here to cities lately, right? That thing is packed with vehicles, burning petroleum, moving our goods and people around. So, great, let's stop burning fossil fuels. Let's build some renewable energy things. Well, new things require new metals. And so with every windmill that we build on the plains of Iowa, for example, it takes 4.7 tons of copper. And unless we're destroying old things to recycle the metals from that, we need new things. We need new metals. Rare earth elements, 2 tons of it. That phrase has made the news lately. Aluminum, steel, concrete, all of these things are required to make those windmills. And if you've driven through these regions, you know there are hundreds of windmills everywhere. And the great work they're doing, we need the metals in order to make them. Electronic vehicles, right? With power and getting rid of fossil fuels, we need electric vehicles, right? We still need to move people around and move things around. Electric vehicles is a solution to that. Well, if we keep making electric vehicles at the rate that we want them, you can see the increase in demand for various metals associated with just the batteries in those vehicles, just to keep them on the road. So things like graphite, nickel, copper, lithium, all those metals are projected to be exponentially more important for that new infrastructure that we want, that we need. The problem is you do have a trade deficit, but it's not the way you think it is. all right? You don't have to read all this. I realize it's very hard to read on the screen. But when you have a blue bar that's maxed out all the way to the right of that image, that means 100% of that metallic resource is imported. And you could see the list. We are not producing a lot of the metals in this country. And therefore, in order for us to build a windmill, to build a new electronic vehicle, we have to have that material come in from somewhere else. And so there is a big trade deficit, all right, that exists because of that fact. But finding metals is not free, all right? It takes a tremendous amount of investment risk to find a new mineral deposit. And this graph is dimensionless in a way, but the vertical axis here is expenditures. And it's a logarithmic scale of increase. Again, it's featureless. It doesn't really matter too much. But finding a new stuff happens on the left side of this image. It's extremely high risk. About 1 in every 500 to 1,000 new mineral discoveries will end up as a mine. The rest of that number is just money wasted because you have to ask someone for that money. So to find new mineral resources, you need investors, and investors, last I checked, don't like wasting money. So you need to be effective with discovering metals. And then we go through the process, and if you get a good one, then you start ramping up expenditures and stuff like that. That's fine. And I'm not even getting into the permitting side of things. I'm talking about purely the discovery of new resources to feed our new needs. Now, as geologists, we know this image kind of well. This is the plate tectonic process, the spectrum of things that's happening on the surface of our Earth that is creating volcanoes and earthquakes and landforms and whatever. And tied to that tectonic process is the formation of different mineral deposits. So things like what I just talked about, copper, zinc, and things like that, they are the VMS on that diagram where we might find something like that. And so we have cartoons like this in all our textbooks, and we teach about this process. And if you take my economic geology class, you learn a little bit more about how these metal forming processes are tied to these different tectonic settings. And while it's all good that we can go to Google Earth right now and find these things, like here's Japan, this is a subduction zone, and these metal forming processes would form in this environment. That's great because it's present day. What we are dealing with, though, when we look at old rocks is this, that same environment of modern Japan, for example, might exist here. And we have to decode that as geologists. But it's not, well, you can see it resembles nothing like Japan now. But billions of years ago, with a B, billions of years ago, that very environment was here. And now it's been deformed and modified and covered up. But recognizing that ore forming environment is what my research does. But the struggle here is that you got maybe 1% exposure of bedrock. You can walk around campus right here. There's no bedrock exposed unless you go to Putnam Rock. And that's your only window into what exists beneath the soil. So, making this an interactive exercise, what exactly does lack of outcrop mean? I got 2 filters. I got a 5% filter, crudely made, and a 1% filter, to show you like how hard it is to recognize things. So let's start. This is a 1% filter on an image that you all know. Any ideas what it is? Centennial. You got some Centennial vote? You saw it's a building though, right? You made an observation. There's a window. Okay, okay. Maybe if I increase it, is that helpful? Maybe a little bit. Now I can see it's outside. I can see a building. Okay. This is the challenge though. This is something you see every day. How about this? He's in the room right now. It's a newer model of that individual. But that's our esteemed department chair, Dr. Scott Clark. You're welcome, Scott. But again, the point of this is not to embarrass Scott, because hey, you were a sharp-looking young lad at one point, I'm telling you. But I mean, in all like seriousness, this is a person's face. And I don't know if any of you in the room can recognize that that was a person's face with a 1% filter, but yet geologists are expected to decode Earth's past with that same filter and make that decoding to actually say there might be a mineral deposit here, and then try to find it. So this is what we're up against. All right, so my motivation of research is that we need metals, period. And recycling is not the answer when you want new stuff, because you don't have the old stuff yet. The new science building is going up. Phillips is still standing. So Zorn, all right, and even the residence halls that are gone right now, even if you recycled all the metal out of those buildings that are eventually coming down on this campus, you still wouldn't have the materials necessary to build that new building. Just wouldn't have enough. And we can't depend on everyone else's metals forever. I don't know if you noticed this, but international relationships are not exactly at an all-time high. And I could do this because I'm Canadian. But, you know, like, it's not a steady relationship. Nothing's a guarantee. As much as I would have said that the Canada-US relationships would have been a lock, yet here we are, okay? So eventually you're going to have to look inside your own borders to discover these resources. And it's hard to find. That red polygon that goes through Carson Park there is the largest sulfide body in terms of the footprint. And well, Carson Park is pretty big. Imagine having that 1% filter on there and flying in a helicopter and sending down poster tubes to try to find it. That's what we're up against as geologists. All right, we are discovering the subsurface from 500 to 2,000 feet up with poster tubes, diameter holes. That's how we're documenting this. Now, maybe if I knew it was a park, I might know where to put that poster tube versus a like a residential area. But that's what I'm trying to do. I'm trying to just define the haystack so then I can start looking for that needle. Another thing that isn't perhaps fair is that ore forming processes are not uniform in distribution in space or time. That means that these environments exist not everywhere on Earth, and they don't last forever. This is Babbitt, Minnesota. I think I'm pronouncing that right. And that gray spot there is an active iron mine that's 1.9 billion years old that formed once in Earth's history that we know of, when cyanobacteria evolved and suddenly there was iron being dumped out of the ocean. So it's only where that one geologic environment existed in space and time where we get those iron formations. But right next to it is a 1.1 billion-year-old nickel-copper deposit that's currently being proposed. Again, a very unique environment that only formed once on our continent at 1.1 billion years ago. Can't help where the metals are, is the story here, right? We have to go after them wherever they are. It doesn't always work to say, not here. So in order to find our metals, we need to improve our knowledge of domestic ore-bearing regions to improve investment risks and find more metals, because again, we need them. Okay, so back to this region, because I've already shown you this map. This region, Great Lakes region, through decades of research, this is the rough geology of that region. So back about 2 billion years ago, this would have looked kind of like the eastern seaboard, just mountains dumping into the oceans, piles of sediment. And then eventually there was a continent-continent collision that brought a whole bunch of stuff together. And specifically of interest to my research is that area of sort of navy dark blue down there, right? That region here hosts at least 150 million tons of copper, zinc, lead, silver, gold mineralization in it that we know of. We haven't fully explored this thing yet. So that region there has become my area of expertise now for I'm in my 11th year here, and I'm still going. And I'm still no closer to any answers, just saying. Well, I got some answers, but what are these mineral deposits? We can find them currently on the ocean floor. In terms of what they look like in drill core, there's sulfide minerals, shiny metallic things that they are copper and all those other metals that I talked about up here bonded with sulfur. and they form on the modern ocean floor. And if the mouse will ever come around, doesn't matter to see it, that there's no talking or anything like that. This is off the coastline in an active tectonic environment, and this is what's on your seafloor right now. They're called hydrothermal vents, or black smokers for short. And these are basically accumulations of these sulfide minerals that happens when seawater gets heated up by magmas and then comes up the surface charged with all these metals. The hot seawater, these plumes of smoke that you're seeing there are about 400 degrees Celsius. They hit the cold seawater and everything dissolved in that comes out of solution because the temperature drop and it precipitates as sulfide minerals. These mineral deposits that we're talking about in Wisconsin are 1.9 billion-year-old versions of this that are now preserved through that mountain building process, now part of our rock record. They only form in deep marine volcanic environments. We don't have the crabs there, by the way. That's the modern one. Let's learn a little bit about this. My goal when I got here, I'm going to attack the one and only deposit that got mined in this region. It's about here on this map. This is called the Ladysmith Rhinelander Complex. I bet you know about where it is in the state now, right? The Ladysmith Rhinelander area. And this is, again, there's maybe 1% outcrop in this region. Probably not even, probably less than that. This is built up with a lot of years of mineral exploration, just interpreting broad rocks and then geophysical patterns and things like that. And really, of all this geology, right, it's this yellow thing in here that's the important target. This is my haystack, okay, if you will, that I need to find and then actually look for the needle in that haystack. And this is what it looks like. There's Ladysmith. And if I had to put a star on there, right, that's the Flambeau zinc copper mine that operated. Well, actually, that's not really accurate. There's the mine. Okay? That's the approximate scale of the ore body that we're dealing with here. Well, it's not operating anymore. Now it's just a nature trail system that you can go walk around, and there's like a horsey play area and whatever. I don't know if any of you guys spend any time up there. This is what it looked like when it was operating in the 90s. Operated from 93 to 97. And I use the analogy of a cupcake. If I gave it to my kid, right, chances are they're just going to lick the icing off the cupcake, leaving the rest of the cupcake on the table somewhere. Okay? There's still some good sugar, a high density of sugar in that cupcake. They just don't want it, right? So that's kind of what the mining company did. They came by, they took the icing off the cupcake, about almost 10% copper, and left the cupcake in the ground. Underneath that park that's just south of Ladysmith, there's still about 5 million tons of what most people would consider high-grade copper ore that's still in the ground. They just took off the icing and left town. So my students and I came in, we did a lot of mapping, a lot of sampling, not through this in terms of walking around the field. Remember, there's no outcrop here. There's 0 bedrock exposures of the Flambeau mine there today, not even in the river. All this work, in terms of this is the mine region itself, the red polygon in there is actually the ore body itself, and then this is a cross-section or a look from the side of that geology. 100% of this figure, and a large proportion of this figure was generated by looking at drill core. And these gray intersections here that you can see on this figure, that is the poster tubes from the helicopter, all right? Trying to define this geologic package, intersect that sulfide ore body, and define it to the point in which investors would actually spend money to get it out of the ground. Spent a lot of time down in Mount Horeb, Wisconsin. That's where the Wisconsin Geologic and Natural History Survey keeps all their drill core. Boxes and boxes and boxes in a warehouse style, and we got all the students going in there, logging core for days at a time. I logged close to 5,000 linear feet from Flambeau alone. It was every stitch of drill core they have. My students and I have looked at it. And we basically rediscover this thing because after the 90s, It's voluntary submission for materials. They don't have to put their core in the core repository. Some of them just threw it in the landfill, right? We go through and describe the rocks. This is the most geology, actually it's not the most geology, but like these are rock names, by the way, for the general audience here. This is something that's called a chlorite schist. It's actually a metamorphosed andesite that you might find at, say, Mount Rainier, all right? This is a quartz ogden schist, which is a metarhyolite, which is something you might find at Yellowstone. And then this is a biotite andalusite schist, which I'm using the word metapelite, which basically means a mudstone. But that mudstone used to be this. It just got altered by all that hot seawater underneath one of those black smokers. So all these different deposits have this sort of alteration package with it, which helps you find them. It's part of knowing which haystack to look in. Now, here's the next big geology thing. Petrochemical associations. This is something developed in the 2010s about looking at the volcanic pile that hosts this stuff and looking at the trace element systematics of that volcanic pile to decipher what tectonic setting this VMS might have been in. So I'm trying to build up a picture of what the volcano was like that actually formed the VMS, or the zinc copper ore body at Flambeau. There are two different possibilities for this volcanic pile. It could be formed in an oceanic setting where everything's underwater or mostly underwater, and this thin little black line gives pretty easy access to Earth's mantle and the metals within Earth's mantle. Or you can have a continental setting where it's kind of built up on the edge of the continent, kind of like what Mount St. Helens is right now, and where those volcanic environments, they might form the same rock types, but they'll form different trace element systematics, and we look at it to actually decode what's happening. For the Flambeau, we discovered that in this, all the different elements that we use to create classification diagrams and things like that, we discovered that Flambeau formed in an oceanic setting. This is actually a cartoon from the tectonic assembly of Wisconsin 1.9 billion years ago. Flambeau formed over here somewhere, not over here. Now, I know this is kind of weird, but what I'm trying to do is trying to paint the picture of what kind of haystack to look for in the rest of Wisconsin, right? This one had a needle in it. So this characteristic now is something I'm framing moving outward. Coming back to the Lake Superior region, back to Wisconsin's geology, this purple one down here got nothing in it, or at least nothing discovered. Does that mean that there's nothing down there? Or if it has all the same characteristics as Flambeau's haystack had, maybe it does have something worth looking at there. Completely unrealized, prosperous terrain for metals. Now, the reason why it has nothing, or at least why no one looked there, is because it actually wasn't part of this system at all. It kind of came in later and then smashed in, and this is the current arrangement of things now in Wisconsin. Here is this marshfield terrain, as it's called. Notice this is not a spelling mistake. This just means it's a block of land with its own unique history that it's now part of the rest of it. That's what a geologic terrain is. And one of the hallmarks of this is that it has coeval or volcanism happening at the same time on this block of land as the VMS forming or the metalliferous stuff over here. Okay, well, why can't it be the same then? Well, let's have a look, okay? So this is the geology of our region. Eau Claire is right there. And this is something called the Eau Claire Volcanic Complex. I bet you didn't know that you had a volcanic complex in your backyard. It's old. It's about 1.9 billion years old, but it's still there. And it's exposed only as river valley outliers. The yellow through here is actually like, it's called the Mount Simon Formation. It's stuff that's over there on Putnam Rock, or what you see in Mount Simon, just sandstones and things like that. It's burying this stuff. But this Eau Claire Volcanic Complex was one of the key areas that was tying the volcanism at Pinokian age, or 1.9 billion year old stuff, to the rest of it. So this is the type locality. It's poorly exposed, never really studied. The only time it was ever described was by Paul Myers in 1980 in a field trip guidebook. He just waded through the river, described the outcrops, and that's it. No additional 21st century data on it to really decipher what it is. So that's what I did. Now you might know some locations in here. This section right here, well, this is Eau Claire County Park, Big Falls. You been? I know the students have. Beautiful little spot. Another area we visited is kind of in this general area right here. Now this one's a little more subtle. It's north of Augusta. It's the North Fork Eau Claire State Natural Area. And this is what it looks like. There's not a lot of anything here. There's no cell phone signal here, which is kind of scary. But the only way to access it really is to, well, get in a kayak. And so that's what we did, which was, in terms of field work, pretty awesome, right? You just splash around the water. It's like a lazy river. You don't really got to paddle. It's 100 degrees out. You're splashing around a river. Great time, great time. Now, I'm going to tell you a little bit of the heartache that some of my students go through getting this stuff. When we get zircons for our next analysis, we talk about we got a bucket of rocks, we do a whole bunch of stuff, and we get down to this. So imagine a beach ball rock, reducing it down to a pinch of salt you put in your food, all right? And then we shoot this with lasers and send it, burn it up in a plasma, and send it over a mass spec. And from that, we do zircon petrochronology. What's another big geology one? But this is looking at zircon, not only ages, but different isotopes and trace element systematics to link tectonic setting with magmatism. And you can get a lot of data out of those little zircons. I know I'm running out of time, so I'm going to push a little bit further here. This is, in case you're wondering, you got a Jeopardy style question, right? This is the age of Big Falls. Then the rocks that are there are that age. But we're discovering things about the Eau Claire volcanic complex that I'm just not going to be able to get in today that actually make it more appropriate to link it with the other stuff that's north than the barren stuff that we talked about to the south. So coming back to this finding haystacks thing. All right, so what are we discovering in my research program? We're discovering that the tectonic history of the Lake Superior region is way more complicated than the classic model suggests. To put it in the haystack analogy, to keep going with that, there are a lot of haystacks, and we're learning which ones might have needles. There are multiple generations of metal forming events that we didn't realize before. So that means that some of these haystacks actually got multiple needles in it that were put there at different times. And what's perhaps more powerful is not necessarily finding out what's going on here in Wisconsin, but this methodology can be applied outward. So we can use the knowledge of our haystacks to help other people find their needles in their haystacks. So next time you're just hanging on a river edge, but know that you're sitting on these old rocks and they're telling a story about metal forming environments. So that's all. The question was, where am I going this year? Where's my group going? We got some really cool stuff in the North Fork area that I kind of want to go back, but there's other river valleys around that I want to do some scouting in. So looking at more of that 1% filter to try to get a better picture of what's going on. So I think this year I'm going up the Chippewa River and then the northernmost part of the Black River to try to pin down where this cool data that I'm finding in North Fork area, how that begins to fill out the picture in other places. That is a loaded question. So the question was, if I could try to paraphrase it for the virtual audience, is that let's just say we find all the metals there is to find in the US. Is there a scenario where we can never have to import anything but also not run out? Is that what I'm getting? Or not even that part, just not import anything? For some period of time, I'd say yes. There's enough diversity of geologic environments that are preserved in the rocks of the US to get most of the metals we need. And so if the border walls went the whole way around and we never looked over them ever again, we could have metals. The difference is now we're in a global economy. And so like even if we can find certain metals, we will be outcompeted at a global stage in terms of where those, so it's going to be cheaper to get them somewhere else, right? But if that shuts down, then things get more expensive, but we could in theory have those metals. But now let's just say we start from scratch, we know where it is, right? Well, for example, that Babbitt mine that I talked about, that's in year 20 of just courts, of just bouncing around in terms of permitting cases in courts, trying to get it out of the ground. They've got all their they know the deposits there, you know how big it is, all the money's been spent. But the permitting stage of things is a whole other argument for some other day.
Just chosen not to, have we had this long history of importing some of these metals because it was just, they found it, right? So it's like, they did the work or they found the metal, so it's easier for them to import it instead of us having to go and try to find it. Is that?
A little bit of that. So there's kind of like this, you know, several decades now, we're just like, we run out of our own resources. The not in my backyard kind of thing, right? It was just easier to let it happen in other places. And so we are getting caught with the pants down a little bit, right? But yeah, it takes a long time to, like, even if we found something here today, it'd be 20 plus years before we can ever pull it out of the ground.
Person is wondering how large the footprints for these deposits are.
Well, I showed you the one, like the largest sulfide ore body. If I go back to show you, this is okay. I think I lost my subtitles here. Okay, this is the largest sulfide ore body in terms of its footprint relative to features that you're probably all familiar with. And so if we were to mine this ore body, it'd be an open pit about the size of the whole Half Moon Lake region, and then plus all the other infrastructure and stockpiles and things that go around that. The Flambeau mine itself is much smaller. It's almost an order of magnitude smaller than this one in terms of, like, you know, absolute size, but like that's about the footprint of this thing. And in terms of its physical footprint, the game with mining is to keep that footprint inside the mine property itself, that the environmental impacts of that are contained in a meaningful way. So it's when back in the 60s and stuff, they didn't care about that, where the footprint was much larger. Modern mining is regulated to keep that footprint contained within that zone. No one wants to think about Half Moon Lake being mined out, but I use that for perspective. There's no giant sulfide ore body underneath there that we know of. Thank you, everybody.